Hi, Thiago Alves here. On the previous video, you saw how to program an Arduino Uno using OpenPLC and ladder logic. Today, we're going to see how to program a Raspberry Pi using OpenPLC as well. The procedure is a little bit different because the Arduino Uno is a microcontroller and the editor can upload the files directly to the board because there is no operating system running on it. The Raspberry Pi, on the other hand, is a full-blown Linux system. We saw together on the second basics how to install the OpenPLC runtime on it. Now take advantage of that runtime and upload a program to it and control the GPIO pins on the board. You'll see how that works and how easy it is to use the Raspberry Pi with OpenPLC. But before we jump in, I would just like to point out the love and support that I'm getting from our sponsors. This video wouldn't be possible without them. If you enjoy this kind of content, please consider subscribing to the channel, liking this video, and also joining our Patreon's program. So let's explore OpenPLC runtime on the Raspberry Pi. So the first thing I'm going to do is to open up Command Prompt, and the same thing would work on macOS and Linux systems as well. Just open up your terminal, and I'll SSH to my Pi. I know it's at the 168.0.60 IP address. Type in my password. And there you go, I'm in. I don't know if OpenPLC is running, so to double check, all I have to do is run system control status OpenPLC, and it's not running. So if I want to start it, I'll have to do a sudo system control start OpenPLC, and then it will start the process for me. I can do a status again. Make sure that it is running. Okay, so now that the OpenPLC runtime is running on the background, I can open up my browser and go to my Raspberry Pi IP address 60 at port 8080, and sure enough, I see my OpenPLC runtime here, and I can log in with my credentials. Oops, I forgot that I had changed it, and there you go. Here is me on the Pi, right? All right, so now let's talk about what project we'll be uploading today. We're gonna make a simple start and stop circuit. So the start and stop circuit is very popular on ladder logic. Basically, it's a simple circuit to start a load and stop that load using two push buttons. For this example, our load is gonna be an LED. And we will need two push buttons attached to two input pins on the Raspberry Pi, right? But let's just check how that circuit works. So I have my two push buttons, PB1 and PB2, and my load attached to it. And you can see that the load itself is closing the circuit as well around PB1. So let's see how the circuit works. If I press PB1, what happens is that it's going to close the circuit between the left and right power rails, turning on my load. Pay attention to PB2, that's normally closed push button, which means that if I'm not pressing it, it's gonna let the current flow through it, okay? So when that happens and the load is activated, the load itself is also closing and closing that gap in the circuit around PB1, okay? So now I can release PB1 and the load is feeding itself, right, through that load contact. Okay, this is a start portion of the circuit. Now when I press PB2, that's gonna open that series sequence of the circuit, turning off the load in front of it. Okay, so when that happens, the load opens up and I go back to the beginning of my circuit. For me to run this on the Raspberry Pi, I will need two push buttons, one LED, and a bunch of wires. Now let's check which pins can I use on the Raspberry Pi with OpenPLC to create this circuit. The easiest way to check it out is go to the OpenPLC project website and then go to documentation and click on runtime physical addressing. Now I'll scroll down till I can see the Raspberry Pi here. And here are the pins that I can use as digital inputs, and these are the digital output options that I have. So for the Raspberry Pi, I'm going to use the first two inputs, which are pins 3 and 5. If I take a look at the Raspberry Pi pinout here, I can see this is what I'm talking about, right? So I'm going to use pins 3 and 5 as inputs, right? That's GPIO 2 and GPIO 3. And if I take a look at the OpenPLC addressing for those, that's going to be IX0.0 and IX0.1. Just keep in mind that for the Raspberry Pi boards, they have included an internal pull-up circuit on those pins. What does that mean? It means that if you're reading these two pins, right, if you don't have anything connected on those pins and you just read them, they are going to return true, right? Because they have internally, they have a resistor connected to it over to 3.3 volts. So they are always reading true, okay? So the buttons you're going to wire to those two pins are actually going to close to ground. So just keep that in mind. That's only true for those two first pins. All the other pins, they don't have anything connected to them. Okay, so we'll use these two pins and we'll also use pin 08 as our output connected to the LED. That's what we are controlling. So pin 08 is right here. That's the first output we can use on OpenPLC. Okay, so you connect the LED on pin 8, you can add two push buttons on pin 3 and 5, and you wire those push buttons to ground. Now, as for ladder logic, let's just open up OpenPLC Editor. And on OpenPLC Editor, I'll create a new project here, just like I did before. And I'll have this project on desktop. Again, I need to create a new folder, and I'll call it My First Pi Project. Make it different from the previous one. And on here, when it asks for the program name, I'll just say start stop. Right, that's the circuit that I'm creating here, start stop in ladder logic. So the ladder logic for this is quite simple, similar to what you saw on the diagram. I will start by creating two power rails. I'd like to add a big one. This is the left power rail. And I will also add another power rail, the right power rail. 50 pins. Okay, I'll just put them together here. Okay, make sure that they are aligned. They are, and I'm all set. So now I can start drawing my diagram. As I mentioned, I'll have two push buttons. So I'll call it the first one PB1. That's of type Boolean. The next one is PB2. Okay, and that is attached to IX0.0. The next one is attached to IX0.1. And then I'll have my load. I'll call it a lamp, or you can call it whatever you want. This one is not attached to IX, it's attached to QX0.0 because that's an output. Okay, now I have my variables. I'm ready to start drawing my circuit. I'll start by drawing a contact and associate that with PB1. And I'll just put it right here and connect it to the left power rail. Then I'll add the other contact and I'll put it negated. Remember on how the circuit works, it is negated because it is supposed to let the power flow through it. Okay, and finally I will close that rung with the lamp itself. Okay, and I have that here. Connect them together. That's my first rung. But then I need to also close the circuit here around PB1. So I'll just put a contact. That contact is associated with lamp itself. And I'll put it right under lamp here. Connected on the left power rail and connected to PB2. Okay, so that's how the circuit works. Let's simulate and see the behavior of it on the ladder diagram simulator. All right, so I'll open up the simulation instance and everything is stopped right now. I don't have any button pressed here. You see that PB2 is normally closed, so current should flow through it normally. When I press PB1, force it true, you see that the whole circuit highlights, right? Its lamp is turned on and that lamp contact is also turned on. If I release my PB1, you see exactly that the lamp is holding the circuit true, right? It's connected in parallel to PB1. So lamp continues true until you presses PB2. When you press PB2, it opens up the circuit, right? And then you can release it and it continues the same. Okay, so that's how the start-stop circuit works. You have one button to start it, one button to stop it. Okay, let me stop my simulation. Now there's a little problem with this thing. I mentioned on the Raspberry Pi the first two inputs are inverted, right? They have pull-up circuits connected internally on the board. You can't change this. This is on hardware, right? So it is pulled up by hardware on those two pins. If I upload a program like this, what will happen is that PB1 and PB2 will be true by default, right? And the circuit won't work as you intended it to work. So what I can do with this is to invert the logic, right? Because it's expecting PB1 and PB2 to be true by default, and they'll be false when you press each button. Okay, so I can invert the logic. All I have to do is to double click on each contact and invert it, right? So PB1 will be negated and PB2 will be normal. So it is the same exact logic as before, just because we're dealing with inverted inputs, then we have to invert the contact state here as well. Okay, so now that we created our program, let's just save this and now I'll generate the program for my Raspberry Pi. I can save it on my disk. I'll call it start stop. Save this. And I'm now ready to upload it. So here's my OpenPLC runtime on the Raspberry Pi. I'll just click on Programs, choose a file, and right on desktop I have my first Pi project, start stop. That's the program that I just generated. I'll upload that program and I'll call it start stop circuit and hit upload program. All right, it compiled successfully. Now I'm ready to run it. But before I start the PLC, it's always good to check if my hardware is set up correctly. Remember that if you're running on Raspberry Pi, you have to enable the Raspberry Pi driver. By default, it comes with the blank driver, which means that it will not do anything on your GPIO pins. So if you upload your program and you just realize that nothing is working, the runtime is running, but your IOs are not behaving as you intended them to do, just check the hardware driver here. You probably need to enable the Raspberry Pi driver by clicking on it and clicking on Save Changes. That will activate the Raspberry Pi driver, making OpenPLC runtime control your Raspberry Pi GPIO pins. Right? Now that I've checked that you have the correct hardware layer driver, just click on Start PLC and the runtime will start. We can see here the logs, everything is running. Alright, so let's see if that works. I've assembled a circuit here. I have PB1, PB2, and my LED. PB1 is connected to the Raspberry Pi over this red wire on IX0.0. PB2 is connected also to the Raspberry Pi over this green wire on IX0.1. And my output here on the yellow wire going from QX0.0 to a resistor. Then on my LED goes back to ground. Right? The other end of both buttons are connected to ground because, as I explained, the Raspberry Pi has an internal pull-up resistor on both of these inputs. So let's see if that works. If I press PB1, I see the LED goes on, which means that the circuit is controlling the load, right? It's holding it true. And if I press PB2, it goes to false. So the circuit works. All right, now that we've seen that our circuit works correctly on the breadboard, what if I wanted to start and stop that load at distance, right? What if I wanted to use a remote station to send a command to turn that load on and off, right? Can I do this? On the last video, we talked about Modbus and the power it has to read and write to its I/O points. Can we use Modbus to remotely trigger that coil? Of course we can, but first we'll have to make a little modification on our program. If we go back to our OpenPLC Editor here, we see that PB1 and PB2 are both attached to inputs. By definition, Modbus protocol won't allow you to write to an input. The inputs are tied specifically to hardware inputs on the device, right? So the Modbus protocol won't allow you to change or modify whatever the hardware is reading on the inputs. So for me to be able to modify the state of those buttons, I will have to change the location of those pins to outputs or somewhere in the QX region. So I can use any QX location that I'm not actively using on the circuit, right? So whatever location that is not QX 0.0 is available for me. I could put something like 99.0 to make sure that I'm far away from any of my usable points, but that would just make addressing a little bit complicated. So just to make this easier, I'll put QX 0.1 for PB1 and QX 0.2 for PB2. Okay, make it simple. Since we're dealing with remote locations, right, we're triggering those buttons remotely, I'll just revert back the logic for the contacts. PB1 is open, PB2 is negated. That brings back my original circuit, okay? Now let's upload the program here to the Raspberry Pi again because we've made those little modifications. I'll just upload to the same file, start stop, okay, replace it, and then I'll go back to my runtime and I will also replace the start stop circuit here. I just need to click on the program here and say that I'm gonna update it and choose a different file, start and stop, upload it again. All right, and it finished compilation. I'll go back to my dashboard and start the runtime again. I have the project running on the Pi. Now what I need to do is use any Modbus software to communicate with my Pi and change the state of those PB1 and PB2 pins. I will just use Ratio as I used before. The only difference is that now, instead of using Modbus serial version, the RTU, I'm using Modbus TCP because I'm on the Raspberry Pi. It has TCP powers, and I will just connect to it over Modbus TCP, right? Over Wi-Fi to make it even more interesting. Now, if I'm using Modbus TCP, I need to provide the IP address of my target and the port. By default, OpenPLC Runtime runs Modbus server on port 502. That's the default port for Modbus. But if you want, you can change it here on settings by entering whatever port number you want. Okay. So let's go back to Ratio. If I have all the settings correct here, I can open up a new data sheet and connection connect. So everything is at 0 here. I can put the names here to make it easier for me to control this. I know that QX 0.0 is LED, and let me open the project here to make it simpler. Okay. QX 0.0 is my LED or my lamp. Let's put the same name here. And QX 0.1 is PB1, and QX 0.2 is PB2. Okay. Now what happens if I set PB1 to true? Okay. set it to true, I see immediately that my lamp goes on, right? And if I look at my breadboard, I see that the LED is also turned on. I can put it back to false, and indeed I see that the lamp remains on. And then if I press PB2, I see that the lamp goes off, and I can put PB2 back to 0, and everything is back at 0, right? So I see that it works. I can remotely control the inputs of my project using Modbus. All right, I hope you guys have enjoyed this video. Don't forget to subscribe and like this video so that I can come up with more content for you. See you guys soon.